Good evening and welcome to this video for the photoelectric effect part 2. Photoelectric effect is part of the level 3 internal standard for modern physics. However, it is also tested at scholarship level at the end of the year. Alright, so for part 2 we're going to be looking at the idea of the photocell, and the idea of the photoelectric effect can be applied to the photocell. So this is when light is incident on the emitter plate. So the emitter plate is basically a metal plate which obviously has electrons and the metal positively charged nuclei. And when light is incident on this metal, photons have a specific energy, and this energy can be absorbed by the electrons, and the electrons can be emitted if the frequency of this light is bigger than the threshold frequency for the metal. These electrons can actually be ejected, and then they can travel to the collector plate, which is the anode, which is going to become the negatively charged plate, and the emitter plate is going to have electrons ejected. So because negative charge is being ejected, the emitter plate is going to become positive, and the collector plate, which is going to collect the electrons, that is going to become negatively charged because it's going to have more negatively charged electrons. It's going to become the anode. So when electrons arrive on the collector plate, it becomes slightly negative, and on the collector plate, when electrons arrive on the collector plate, it becomes slightly negative, and on the emitter plate, so I should say on the emitter plate, it becomes slightly positive. So this causes a potential difference to be generated. So there's a potential difference. So this one plate is positively charged, the other plate is negatively charged. There's a potential difference. Therefore, if we connect it into a closed loop, if we have a closed loop connected to the plates, then we will actually have a current, a very small current that is generated, and this is known as the photocurrent, and it can be measured using a sensitive ammeter. So here we have a diagram of what I was just explaining. So we have a light source which can be shone onto the collector plate. Electrons are ejected from the collector plate, electrons are ejected from the emitter plate, and they travel to the collector plate. And then the emitter plate will become slightly positive, and the collector plate will become slightly negative. This causes a potential difference, and hence a photocurrent to be induced in this circuit. Right, so the stopping voltage. So the stopping voltage is the minimum voltage that is required in order to allow the current in the circuit to be 0 amps. So this can be done by setting up the electric field between the collector and the emitter plate. So electrons have to do work against the electric field in order to reach the collector plate. So when we have the light incident on the metal, electrons are going to be ejected with a specific amount of kinetic energy. However, work has to be done by the electrons against the electric field in order to reach the collector plate. By doing this, some of the kinetic energy of the electrons is lost and being transferred into potential energy. So the stopping voltage is a minimum voltage that's required so that the electrons do not reach the emitter plate. If there are no electrons reaching the emitter plate, then therefore there can be no current in the circuit because there's no potential difference. Because potential difference can only occur when there's a difference between the charges on the plates. But since there's no charge arriving on the collector plate, then therefore there cannot be the current that is generated there. So the work done is equal to the voltage times the charge, but in this case the charge on the electron is just E. So work done against the electric field is equal to the charge on the electron times the voltage. So here I have a diagram of what I was talking about. So we have our light incident on our emitter plate, which ejects the electrons. However, it is doing work against the electric field, and therefore some of its kinetic energy is going to be transferred into potential energy. And this voltage, the stopping voltage, is the minimum amount of voltage required in order so that the electron just doesn't reach the collector plate, and therefore there's no current in the circuit. So here are some equations. So we're going to derive some equations. So from part 1, we know that the maximum kinetic energy of the electrons is purely the difference between the energy of the photons and the work function of the metal. So we were talking about how the minimum amount of energy in order for electrons to be ejected is the work function of that metal, and each metal has its different work function, and the amount of energy that a photon has is simply equal to hf. So some energy is going to be used in order to bring the electron to the surface, and all the remaining energy that is left over will be converted into kinetic energy, which allows the electron to move away. This is the maximum kinetic energy because not all electrons are being ejected at this velocity, and that's because this is the maximum kinetic energy occurs when on the electron, which requires the least amount of work to be done to bring it to the surface. However, some electrons will require more work to be done in order to bring it to the surface of the of the metal, and therefore it will have a lower kinetic energy when moving away from the metal. So in this case, our maximum EK equals to energy of the photon minus work function, which is HF minus the work function. So when the stopping voltage is applied, all of the kinetic energy is converted into potential energy. This is because the electron does not reach the collector plate. If the electron does not reach the collector plate, all of its kinetic energy is going to become potential energy. So we know that the work done is equal to E times V. And therefore, we can say that E times V equals to the maximum kinetic energy of the electron. And therefore, we're going to have our stopping voltage is equal to the frequency of the light that's incident on the metal times the ratio of Planck's constant and the charge on the electron minus the work function divided by the charge of the electron. But as you can see, this graph is in the form of y equals to mx plus c, which is a linear graph. So however, we know that the work function of the metal is equal to the Planck's constant times the threshold frequency, because the threshold frequency is the minimum frequency required to eject electrons. Therefore, the voltage is equal to frequency of the light times of h over E minus h times the threshold frequency over E. So here's the graph analysis. We have our stopping voltage on our y-axis and the frequency on our x-axis. So once again, this looks very similar to the kinetic energy against frequency graph we were looking at in part 1. So the x-intercept is the threshold frequency, so therefore the stopping voltage is 0. The reason that the stopping voltage for the threshold frequency is 0 is because the threshold frequency corresponds to the work function that is required to bring the electron to the surface of the metal. Therefore, once the energy of the photon for the threshold frequency is absorbed by the electron and is brought to the surface of the metal, there is no more energy that is able to be transferred into kinetic energy. And because there's no kinetic energy, the electron isn't going to move anywhere, and therefore there's no stopping voltage needed in order to stop it from reaching the collector plate, because it doesn't have a kinetic energy to start off with. Okay, so the y-intercept is negative h times the threshold frequency over E, or the work function over the charge of the electron, and the gradient in this case is the ratio of Planck's constant and the charge on the electron. Alright, so here are some practice questions. So what stopping voltage must be applied to a photocell of a potassium emitter if its incident light has a wavelength of 350 nanometers? Alright, so the potassium work function is equal to 2.2 electron volts. Alright, so I'll give you some time to work out the answer to this question, and when you're ready, keep watching the video to find out the answer. Alright, so the first step for these types of questions is always we need to be calculating the frequency of the light, because in this case we have the wavelength. We need to find the frequency in order for it to be related to the energy of the individual photons in the light. So therefore, step 1, calculate frequency equals to V equals to F lambda, and we can find the frequency equals to 8.571 times 10 to the power of 14 hertz, because the speed of light we know is 3 times 10 to the power of 8. Alright, so step 2, we can apply our derived formula that we just applied. So that's the V equals to frequency times h over E minus the work function over E. So in this case, we can write down our derived formula. And remember that the energy is always in the energy is in joules. Okay, so in this case, we're going to be converting electron volts to joules. So 2.2 electron volts is equal to 3.52 times 10 to the power of 19 joules, and that's equal to the work function of potassium. In this case, we already have all our information. We know frequency, we just calculated. We know the Planck's constant, we know the charge of the electron, and we now know the work function, so we can calculate by plugging all the numbers in. And at the end of the day, we should get that the stopping voltage is equal to 1.35 volts. Therefore, a voltage of 1.35 volts needs to be applied in order to ensure that the electrons do not reach the emitter plate. Okay, so. Right, so now have a look at example number 2. So Kevin does an experiment with 80 nanometer light incident on a zinc emitter with work function 4.2 electron volts. He carries out 3 trials to determine the stopping voltage. So use the information to calculate the theoretical Planck's constant. Right, so here are the 3 trials. So stopping voltage, trial 1 is 11.44 volts, trial 2 is 11.47 volts, and trial 3 was 11.41 volts. Alright, so we'll give this question a try, and when you're ready, keep watching the video to find out the answer. Alright, so first things first, we've got to find out the frequency of the light that's incident on the zinc emitter. So we can use our V equals to F lambda in order to find out our frequency. So to find out our frequency, we use V equals to F lambda. We know the speed of light is 3 times 10 to the power of 8 meters per second. We know our wavelength is 80 nanometers. So we substitute that in and we'll see that frequency equals to 3.75 times 10 to the power 15. Should be hertz, why does it say joules? Okay, so it should be F equals to 3.75 times 10 to the power 15 hertz. Second of all, we need to find out the average stopping voltage from the three trials. Okay, so three concordant trials, we're going to find the average. So the average, we're going to add them up and then divide by 3, which is the number of trials. And we get the average is 11.44 volts. So now we can substitute our stopping voltage is 11.44 volts. Our frequency incident light is 3.75 times 10 to the power 15 hertz. And the work function for the zinc is 4.2 electron volts. So we can substitute those numbers in. So we can say stopping voltage is equal to our frequency times the ratio of Planck's constant over the charge on the electron minus the work function over the charge on the electron. And we know that we can convert 4.2 electron volts to joules by multiplying by 1.6 times 10 to the power negative 19. And we should find that the Planck's constant should come out to be 6.673 times 10 to the power of negative 34, and that should say joules seconds. Okay, so because E equals to Planck's constant times frequency. Frequency is measured in per second, and energy is measured in joules. So it actually should be joules seconds, not joules per second. That's my mistake. So Planck's constant at 6.673 times 10 to the power negative 34 joules seconds. Alright, so example number 3. 5,000 terahertz, that's 10 to the power of 12. Light is incident on a cesium emitter plate with work function is 1.4 electron volts. Our resistor is connected to a circuit with resistance 3 ohms. How many electrons will reach the collector plate before the stopping voltage will prevent the electrons from reaching the collector plate? And what is the maximum current in the circuit? So we're going to assume that the plates can be modeled roughly with a capacitor, with the capacitance is equal to 12 times 10 to the power negative 6 farads. And so give this question a try, and when you're ready, keep watching the video to find out the answer. Alright, so first thing first, we can find out the stopping voltage required to prevent the electron from reaching the collector plate by using our formula we derived. So that is our stopping voltage equals to frequency of the light times the ratio of Planck's constant and charge on the electron minus the work function over the charge on the electron. We know all our numbers because we know that our frequency is 5,000 terahertz, that's times 10 to the power of 12. We know Planck's constant, and we know our charge on the electron, and we know our work function is 1.4 electron volts. If you convert it to joules, you get 1.4 times 1.6 times 10 to the power negative 19, and you'll see that voltage should come out to be 19.31875 volts. And it's important to make sure you have a large amount of significant figures. That's because the charge on the electron is very small, so by the time every significant figure will be pretty significant in the final answer. So we're going to assume that the plates can be modeled by capacitor. Capacitance is 12 times 10 to the power negative 6 farads. So that's going to, the amount of charge is going to build up as the electrons move from the emitter plate onto the collector plate. The charge will build up on the collector plate, and it will become negatively charged, and the loss of the electrons from the emitter plate will make it positively charged. This will cause a potential difference, and this potential difference is dependent on the capacitance and charge stored. Okay, so in order for the capacitor or the two plates to have a potential difference of 19.31875 volts, which is the stopping voltage required to prevent the electrons from reaching the plate, we can substitute the stopping voltage and the capacitance to find out charge. So that's the charge needed on the plates in order for the stopping voltage to be achieved. And now we can find that the answer for the charge is 2.31825 times 10 to the power of negative 4 coulombs. And we can actually find the number of electrons because we know the charge on one electron is negative 1.6 times 10 to the power of negative 12. But we can use the positive in this case. So in this case, we can actually find the amount of electrons by dividing the total charge over the charge on one electron. And we should see that the number of electrons is 1.44891 times 10 to the power of 15 electrons. We also know that the stopping voltage by the time that this happens, so by the time that no more electrons will reach the collector plate is when the stopping voltage is achieved, and the stopping voltage is 19.31875 volts. So by the time there's a potential difference on the capacitor plates of 19.31875 volts, this will be the voltage in the circuit, so therefore we can substitute those numbers in. So the resistance we know is 3 ohms, and voltage is the stopping voltage, and we should find that our current is 6.44 amps, and that's our final answer. Alright, so now we're going to move on to some scholarship concepts. So this is de Broglie's wavelength. So Broglie proposed that matter, like light, has both particle and wave characteristics. So his argument was as follows. So wave-like properties of light have wavelength, so that's waves have the wavelength, and particle-like properties have linear momentum, so that's its mass times its velocity, P equals to mv. We're very familiar with momentum from level 2 and level 3 physics. So he found that we can actually link the wavelength with the linear momentum by using Einstein's E equals to mc squared. So he found that the wavelength is inversely proportional to the linear momentum. So we know that E equals to hf, that's the energy of the photon, that equals to mc squared, because E equals to mc squared, and we can say that the linear momentum is equal to its mass times velocity, but we know that the speed of light is c, which is 3 times 10 to the power of 8. So in this case, we can substitute p squared. Okay, so p squared, sorry, not p squared, p equals to hf over c, and we know that v equals to f lambda. So v equals to f lambda, therefore f over c, we can substitute that as 1 over lambda, so therefore that will give us p equals to h over lambda. And if we rearrange to find for the wavelength, we'll get wavelength equals to h over p. Alright, so de Broglie's wavelength of electron acceleration through a potential. Okay, the de Broglie wavelength of an electron accelerated through a potential difference can be calculated by linking the momentum to the kinetic energy. So we know that the kinetic energy of the electron is equal to half mv squared. We know that the momentum is p equals to mv, and therefore p squared, okay, so taking the square of both sides, we'll get p squared equals to mass squared times velocity squared. And if we substitute p squared in, we'll get ek equals to p squared over 2m, because p squared equals to m squared v squared. We have mv squared in our ek, so therefore ek equals to p squared over 2m. So therefore, if we rearrange for p squared, we'll get 2m times the kinetic energy. However, we also know that the loss of the electron, because the electron is accelerated through a potential difference, we know that the loss of the electron the loss of the electric potential energy is equal to the kinetic energy gained by the electron. So therefore, the kinetic energy is equal to a potential energy that is lost, which is equal to the charge of the electron times the potential it is accelerated from. So therefore, EV equals to EK, and we can put that into our equation. So P equals to square root of 2 times the mass times the charge on the electron times the voltage it is accelerated through. Right, so here's an example question. So what is the de Broglie's wavelength for an electron accelerated through a potential difference of 1000 volts? So this one we can just, mass of the electron is 9.11 times 10 to the power of negative 31 kilograms. So give this question a try, and when you're ready, keep watching the video to find out the answer. Alright, so we can just use our equation that we just derived, so that's our momentum equals the square root of 2m times charge on the electron times the potential. And we can actually find that by plugging in these numbers, we'll find that momentum equals to 1.7074 times 10 to the power of negative 23 kilograms meters per second. And because de Broglie linked the momentum, linear momentum, and wavelength, we can use his formula in order to calculate the de Broglie's wavelength. So that's the wavelength equals to Planck's constant over linear momentum. That's how he linked the wavelength with the linear momentum. So therefore we get that the wavelength is equal to Planck's constant divided by the linear momentum, and that's lambda equals to 3.88 times 10 to the power of negative 11 meters. And that's the de Broglie's wavelength for an electron accelerated through a potential difference of 1000 volts. Alright, and that's it for this video. I hope you enjoyed watching this video, and I hope to see you on the next one. Thank you, bye.